Hello everyone, and welcome to the Game Engine programming series where we write a game engine from scratch. In the last two episodes, we looked at the theory and implementation of environment cube map pre-filtering for image-based lighting. We saw that the pre-filtering result comprises of two components, namely the diffuse and specular components. The diffuse component is simply the cosine-weighted average of all pixels on a hemisphere in the direction of the surface normal. We used the split-sum approximation method for the specular component, which consists of a cube map with MIP levels that depend on the environment image and the surface roughness, and a lookup texture that depends on view direction and the roughness. We implemented support for pre-filtered environment maps and wrote compute shaders for pre-filtering the diffuse and specular parts, except for the lookup texture. So that's what we start with in this episode, and as before, we look at the compute shader code first. Here I added a new shader function that writes to a simple 2D texture. We call integrate BRDF function for each pixel. The UV coordinate in the x direction is a value between 0 and 1, which represents the cosine of the angle between the normal and view vectors. The UV coordinate in the y direction is also a value between 0 and 1, representing the roughness value. The function returns two floating point numbers, which are written to the red and green channels of the corresponding pixel in the lookup texture. We already discussed this BRDF integration code in the previous episode. Here we construct the view vector from the n.v parameter. This is a polar to Cartesian coordinate transformation where n.v is the value of theta and phi is set to 0. In the for loop, we have the implementation of the sum as a result of importance sampling. For each sample, two uniform random values are generated using the Hammersley sequence. Importance sample ggx will map the random values to non-uniform theta and uniform phi angles and construct a half-wave vector by converting the angles to Cartesian coordinates. Reflecting the view vector over the half-wave vector will give us the light vector. We can use these vectors to calculate other parameters needed for evaluating the geometric term, which in our case is the Smith height correlated geometric function. This is again an exact copy of the one we used for physically based rendering. I also added another function that calculates power of 5. Now we have everything to evaluate these two sums. We put the results in a and b variables. After the for loop, we average a and b by dividing both of them by the number of samples. Note that we skip calculating a and b if n.l is 0 or negative. We do still count them as samples with 0 contribution to the sum because the light is blocked by the surface. Therefore, we still divide by the total number of samples. As I mentioned in the last video, I was going to clean up the prefilter envmap function, which does the specular component of the cube map. Here I renamed some of the variables and added comments from the Frostbite paper in order to explain this mipmap selection. And that's everything that was added to the shader code. So I'll now show the whole file for completeness. Next, I added the shader name in the batch file for compilation in the same way as for the other shaders. This produces a byte array in C language, which we can include in our C++ code in envmap processing.cpp. Nothing else was changed except for the addition of a new function that runs the new compute shader. This function is simpler than the ones that we wrote before, since we don't have an input texture and the output is a simple 2D texture. So we only have to create a texture 2D that's only GPU accessible, and another one that's also CPU accessible for downloading the result. The output texture has a size given by this constant, which is 256 and has a 16-bit floating point format. We could probably get away with a smaller texture without losing image quality, so feel free to experiment with different sizes. Again, we set the unordered access flag for this texture so that it can be written to in our shader. For the CPU accessible texture, we set the CPU access flag accordingly. Creating the shader, the constant buffer, and the sampler all happen in the same way as in the other functions. We can also set the shader constants, which are just the size of the texture and the number of samples. Like I said, we don't have a cube map or texture array or any mipmaps to deal with. So there is no for loop and we can just dispatch the compute shader once. Therefore, we create an unordered access view for the output texture and calculate a block size as before. At the end, we download the result into a Scratch image using this function which I already explained in past episodes. We add a forward declaration for the new function in textureimporter.cpp in order to be able to call it. Here we use the result of runOnGPU function instead of only checking the HR value, which I did as a little improvement. And I added a new function that can be called by the editor for generating the lookup texture. It's fairly simple and only calls the BRDF integration function with a sample count and returns the result to the editor. Remember that this texture doesn't depend on any input image. Therefore, we only have to generate it once and use it for any environment cube map we like. This function is imported in content-tools-api.cs and we can call it like this to create the texture. Note that we don't want to compress the texture and it doesn't need to have any mipmaps. When the function returns, we can check if it was successful and if so, return the results by calling texture-setData. Now, because this is not a part of the process of importing a texture, we have to call this method somewhere at least once in order to create the lookup texture. I thought it would be nice to have a place for all assets that are independent of the game project, also known as default assets. For example, we would like to have a default material for a mesh object that is loaded in the scene before the user has assigned a material to it, or a default cube or texture whenever a mesh or texture couldn't be found for any reason. So I created a static class with a method that creates these default assets if they don't already exist. This method is called at startup of the main window. Here we can see how the path to the default assets is determined. I'll explain this in more detail in one of the next videos, since I'd like to concentrate more on the C++ code in this video. But the general idea is that we use a resource folder in the same directory as the editor's executable and put all default assets in that folder. The BRDF lookup texture is one of the default assets and therefore we can create it if it doesn't already exist. And here's the method that simply calls the Content Tools API for creating the texture, which can be accessed through this property after it was saved in the default assets folder. We also create a cube that can be a placeholder for any geometry asset that couldn't be found, because it's essential to have a fallback geometry in games in order to look professional. Like in this example, it would be awkward if there was nothing attached to the web, right? It wouldn't make any sense at all. All is good, however, with the default cube geometry. I also moved the project templates to this new resource folder. Like I said, we'll look at this part of the code in a later video. Starting the editor, we see that two new assets are generated. Normally, the editor would handle when these assets are used, but for now we can just copy them to our content folder so that we can inspect them. Here we see the cube mesh and the lookup texture, and we can open each one like any other asset. Opening the lookup texture, we can see that it's a 256 by 256 texture using a 2-channel 16-bit floating point format. We can look at each of the channels separately. Also note that we can't re-import this texture since it doesn't have a source image. Now that we have all pre-filtered textures, we are going to send them to the engine and use them for image-based lighting. Since we are using an image to approximate a global light source from the environment, we can use it as the ambient light source. Therefore, I added a new light parameter struct in the renderer.h next to the other light parameter types. It's included in this union within the light init info structure. Because there can be only one ambient light per light set, we can send the light data to the GPU in the global shader data buffer. We defined this buffer in the common types shader include file. Here we see that this section is removed, and that's because it's moved down here, where we can see a new struct for ambient light parameters. It has an intensity and 3 descriptor indices, which are used for indexing into the shader resource view descriptor heap, as we'll see later in this video. These are included in the global shader data. Note that we can't simply append it to the end of the structure because of the constant buffer packing rules. Basically, everything is packed in groups of 4 32-bit values. Here is an excellent blog about constant buffer packing rules. The per-object data structure is unchanged, and I added an assertion for making sure that the data sizes are a multiple of 16 bytes. In addition to what's needed in order to support image-based ambient lights, I also removed the base implementation of the forward plus light culling algorithm. I think by now we are quite sure that our implementation works well and we don't need the old reference anymore. So everything here that's used without bounding spheres is removed. Please watch these videos if you'd like to know more about forward plus lighting and light culling as implemented in Primal Engine. In this file, we remove the 4-plane frustum type, cone radius and light type in light culling light info, and the light type in light parameters. And here is the entire code of common types.hlsli. In common functions, only these 2 functions were removed. In grid frustums, I deleted the compute shader that was using the 4-plane frustum algorithm. In calllights.hlsl, I removed this function since we calculate the cone bounding spheres in the C++ side. And I removed the old compute shader for light culling. Going back to the image-based lighting, we have a new light type for ambient lights. We can add an ambient light to a light set defined in the 3d12 light.cpp. Since we need to get hold of the descriptor indices of the pre-filtered textures, we have to include the content header here as well. Now we have an instance of ambient light parameters and the ambient light ID for each light set. These member variables are set where we add an ambient light. First, we get the descriptor indices of the 3 textures and fill those in the ambient light parameters structure. Then we create a light owner using the provided entity ID and the light type. However, the light data ID is set to invalid ID since there is only one ambient light and we keep its data in this member variable. We add the light owner in the list of owners and keep its ID in another member variable. Finally, the light is returned with the ID and light set key. We don't have to do much for removing the ambient light. The member variables are reset and the light owner is removed as for the other light types. Enabling and disabling the ambient light happens in the same way as for directional lights. The intensity can be set directly for the ambient light. Here I removed code that was only needed for the old light culling implementation. I added a new member function that returns the ambient light data if the light is valid and enabled. We might want to optimize this a bit so we don't have to check for validity every frame. Here is some more removed light culling code. and the member variables which we've already seen. Finally, we have a function that will fetch the ambient light data for a given light set. We have to declare this function in the 3D12 light header file. Here, the ambient light parameters type is forward declared, since the function returns an instance of this type. The ambient light data are put in the global constant buffer using a single function call in the 3D12 core.cpp. Now we have done all that's needed for creating an ambient light and sending its data to the GPU. Let's create such a light in our test application. I did this in renderitem.cpp instead of lights.cpp because we have the code for loading textures in this file and I didn't want to spend time sharing it. Also, it's easier to have all of the load operations at one place. Here I added 3 IDs for the pre-filtered textures and a variable that holds the ambient light. I wrote a function that creates an ambient light using the texture IDs. Here I didn't bother creating a game entity and just pass 0. It doesn't really matter since we don't do anything with the game entity for ambient lights at this time. When loading the assets, we load 3 new textures. I'll show you how to create these files later in this video. After everything was loaded, we create the ambient light. The light is removed at shutdown, and the textures are unloaded as well. Looking at lights.cpp, we see that we create light sets here before creating lights. The engine needs to have at least one light set before we can add any lights. Since the light sets are created here, we have to create the ambient light after we call generateLights function. That's why I moved the function call before calling createRenderItems where the ambient light is created. The same holds for removing the lights. All lights need to be removed before light sets are removed. At this point, we have successfully loaded the textures and sent their descriptor indices to our material shader. All we have to do now is to sample from the textures and evaluate the sum for image-based lighting. This is done in our test shader, where I also added this new member in the surface data. It doesn't really have anything to do with image-based lighting, but I just wanted to play with fine-tuning the strength of specular lighting in general. We are going to sample from textures using specific MIP levels that depend on the surface roughness. Therefore, I added new overloads for the sample function. We can use these to sample from 2D textures or texture cubes. Here's just a bit of code cleanup in calculateLighting function. Then we finally arrive at the part where we have been doing all this work for, which is evaluating IBL at a pixel given by surface S. It's got some commented code because I was playing with it earlier and I forgot to remove them, so let me do that now. This function looks a little bit more complicated than the one we looked at in the explanation video about pre-filtering the specular component, and this is for the sake of a better image quality. First, we have to make sure that n.v is a value between 0 and 1. We also need to approximate the specular color at grazing angles, which is called f90. I honestly can't remember where I got this approximation from, but it works well as far as I can tell without having a reference image. Optionally, we can also calculate the Fernald term so that we can subtract it from the diffuse part in order to account for the specular reflection at grazing angles. The roughness alpha is calculated next. We need it as a parameter for this function, which gradually shifts the light vector towards the surface normal as the surface becomes more rough. Normally we would just calculate the light vector by reflecting the view vector over the normal vector and use that for sampling from the specular cube map. I'll show you the difference in the next video where we are going to concentrate on improving the image quality. The last texture to sample from is the BRDF lookup texture, where we use n.v and the perceptual roughness as the UV coordinates in order to get the pre-calculated sums in the red and green channels. The specular component is then given by this expression, where I added the specular strength as an extra parameter. At the end, we add the diffuse and specular components together, multiply by the intensity, and return the result. I skipped over this part for now, which we'll discuss in the next video. In getSurface function, I moved clamping the roughness value to the end, so we don't have to repeat this. The value for specular strength is 1 for metals and becomes increasingly small for rough non-metals. This is something I added myself and it's not physically based, so you can feel free to leave it out if you want. I cleaned up the main function of the pixel shader and again removed the old lighting functions that were only used for the forward plus base implementation. Looking at the shader code as it is now, we see that we can turn off all lights using conditional compilation in order to only have the image-based lighting. Normally we want to combine the two lighting methods, but for now I just wanted a quick way of switching between direct lighting and IBL. So right now with IBL enabled, we can have a look at the result. Although first we have to save some textures for the test application. Using the editor, let's import these 3 textures as pre-filtered cube maps. We can inspect these textures in the content browser. Okay, let's do one more. Now we have 4 environment maps that we have to place somewhere the test application can use them. In renderitem.cpp, we see that it's going to look for the textures in the IBL folder. So we have to create these folders and files. We have 4 sets of images, so I'm going to make a folder for each set. Remember that opening a texture will save it for the test application, and we can simply copy and rename the files. The lookup texture can be used with any image, so we copy that to the root IBL folder. Before copying the other 3 images, let's try and see if all our efforts from the last 3 episodes paid off anyway. And here is our first render using image-based lighting. Well, it looks interesting, but there are some issues that we need to fix and improvements that we can do for a better image quality. We are going to do that in the next one. Hopefully you enjoyed watching this video. Thank you as always for joining me, and I'll see you next time.